Since 2018, we've been supporting the design of 5 to 6 systems in a package, mostly for military applications. We have acted as Thermo-Mechanical and structural dynamics subject matter expert, both supporting the aspects of manufacturability as well as military compliance to requirements and even space requirements sometimes, depending on the customer. At this point, we have 6 designs that have been produced, have been validated and qualified. Some of them already in place, and we see on the right, we see an example of one of those components. In order to perform those support activities, we make extensive use of the MSCOne product line, the tool set that comes with MSCOne. It starts early on with PICLS for thermal custom validation of initial conceptual designs, to MSC Apex to create detailed models for further analysis, being shock and vibration, or MSC Marc at CAEFatigue for more complex analysis, including BGA, so solder joint fatigue analysis and strain calculations. We also use scSTREAM for finalizing the designs in terms of thermal performance, both at the package level and the higher level assembly. System military systems, being a single board computer or even the entire system. So on the agenda today, I'm going to spend a little bit of time introducing our company and introducing myself. Also presenting the tool set that we have, that we use in the company as far as MSC is concerned. Then we're going to move on to describing a little bit what is a system in a package. SiP, we're going to call that SiP for the rest of the presentation. What it looks like, what it's supposed to do, and what typically we're expecting it to do in terms of requirement. And then after that, we'll kind of show the examples, go through the motions of what we do with MSCOne, particularly in the context of this SiP. MSC Apex, MSC Nastran, CAEFatigue, scSTREAM, and others. So TECH LLC as a company, we were founded in 2011. We're in our 11th year. We started in Los Angeles, California. We've expanded, we have moved. In general, the company has grown double digits since its inception. We have about 95 to 98% customer retention and repeat business. We support primarily the U.S. defense contractors, either at the prime level or second tier level, and sometimes third. And we also perform our own design in R&D prototyping. We'll talk a little bit later about that. The majority of what we do and the expertise we bring to the table is in structural dynamics and thermal management. Principal industry being aerospace and defense, defense electronics, rugged electronics, RF and microwave components. For those applications, we usually perform shock and vibration, fatigue and durability. So at the component level, at the subsystem level, at the system level, and sometimes even at the vehicle level. I also perform a lot of thermal management and electronics cooling, either verification or improving thermal designs or coming up with ways of cooling things that are pretty challenging. And again, as I mentioned earlier, we also have our own R&D and prototyping little shop, little lab. We have a couple patents that we're working on still in the design electronics, rugged electronics world. We also are rugged recommended design and analysis airflow by provider, which is a particular design of a single board computer with specific requirements for airflow and specific design for airflow control And we also brought, about a couple of years ago, we started building our own quadcopter sensor integration demonstrator. We call that the Huracan. It was used for ballistic testing and sensor testing. And this is something that we developed and assembled and put together. So we have also knowledge of hardware and hardware development. So personally, I am one of the founders of the company. I manage the technical aspects mostly of the company, starting from what we should do, how we should approach problems, what tools to use. We've run a lot of benchmarks, being for software, hardware. Do a lot of project management naturally and customer relationship management, and manage the team, performing all the analysis in most of the design. I come from the European aerospace industry, namely Eurocopter Aerospatiale. Worked on as either dynamics engineer or structural engineer on helicopters and different airframes, missiles, and space launcher, including the Ariane 5 space launcher. I've then moved to the US and worked in a certain number of companies. EDS, for instance, STRC, one of the older CAD CAE companies. And I've been in the industry for about a little bit less than 30 years, so just about 30 years. As far as what MSC tools we use in our company, we've been using MSC Apex since 2016, MSC Nastran also since 2016, but really personally have used it since version 66, so really 20 some years. And scSTREAM, which was our solver before MSC acquired Cradle. So we've been pretty proficient at it for about 10 years now. All of those tools replaced our existing tools that were very well regarded, that had good users, that we were proficient with it, and all of those tools just outperformed everything by 2 to 5x. So for us, it was a no-brainer. We just switched tools. Now we're going to spend a little time talking about SiP, a system in a package, and what it is. Basically, this is a bunch of components that should be distributed on a PCB that are actually all brought together in a smaller package, performing the same task, and sometimes even more than a traditional PCB. And instead of having one die, one substrate, another die, another substrate, all this put together on one board, you have one little substrate that contains all of this. So this offers many benefits. First of all, size-wise, it's much smaller. So therefore, we have a signal speed up. We have, all the wires that are shorter, that goes faster. We can increase functionality, and more importantly, we can have multiple of those in a PCB now instead of just a single set of components spread around the board. So this whole concept, it's not new, but it's coming to fruition now because of the new technologies, because of the ability to model this and design this very well nowadays. But this is driven by two set of industries. The first industry is the consumer products, and really all the autonomous vehicles, electric vehicles, and some telecom. And the second application is all the military demand. Military is all about what they call SWaP, size, weight, and power. So we see how we solve the size and weight instantly with this kind of packaging. If we look on the right, we see an example. This is an FPGA from Xilinx. So this is the Vertex 7. So you see different applications being performed by different dies. You see, so that what we call an interposer. We'll see that later, a substrate, and different dies performing different applications. As far as our design requirements, we have multiple thermo-mechanical challenges. The substrate interposer, the BGA materials, all of this have to play together, have to be connected. The interconnections have to be sized properly, the BGA pitch, the size of the balls. We need to take into account the fact that we are manufacturing things step by step. And each of those steps include raising the temperature to a 200, 300 degrees sometimes, and cooling down to make sure everything settles. And we have also to manage the thermal aspects of all of this as far as operational thermal management, internal to the package and external into the upper level assembly. And to make things even more difficult, now we're operating in a military environment, which has, a lot of harsh environment, shock, vibration, low and high cycle fatigue, requirements for reliability over a decade, sometimes more. The first thing we're going to look at, the first decisions we're going to have to make are typically what kind of materials to use and how to attach them, and those are all driven by the manufacturing process. Each material that we choose impacts the next one, and the stack up has to be thought out. The type of solder that we use has to be carefully decided, as they have different temperature limits, different behavior, different stiffnesses. All this impacts shock and vibration, as well as thermal, as well as simply manufacturability. Similarly, the thermal management itself. So thermal management becomes important almost the first day of the design. Can we even cool this thing? How much cooling do we need? Again, those products can range from 100 to 300 watts, sometimes 400 watts, depending on what FPGA and what die we use. So we need to quickly evaluate what we're going to need to cool this down. We don't necessarily know right away in what kind of platform that's going to go. And that's probably one of the biggest issue, is those products are initially designed to be fairly universal. But when you start having 200, 300 watts to dissipate, this universality kind of goes out the window very quickly. You're left with only a few options, like liquid cooling or forced convection or heat pipes. You can't necessarily rely on simple free convection, natural convection to do the job. Same thing, we also look at what kind of thermal interface material you would need for your heatsink. So all this preliminary design is typically done in PICLS, simply because it takes 3 seconds to set up. Again, the geometry is very simple on a SiP. It's a bunch of rectangle already, if you put it simply. But organizing those rectangles in a manner that actually pleases the thermal engineer and the electrical engineer, we can't forget those guys. It's not necessarily easy. And, very quickly, PICLS let us see, well, if you're in a free convection environment, it's never going to work. You need a minimum of 4 meters per second airflow at X70C or something like this to actually come close to a possible design. So we already know this very quickly after using PICLS for a little bit, and we can move on to higher level thermal analysis using Cradle CFD, so scSTREAM. This allows us to have a good idea of what we want before we start the complex 3D modeling. Once we move to scSTREAM, so we can perform more traditional thermal analysis, as in, is it going to work? Is it going to be too hot? What's going to be too hot? What can we do? And also, we also performed JEDEC types of calculation. So those allow us to provide a supplier, for instance, a set of values, thermal resistance, to plug directly into their thermal model without having us to provide anything but those calculations. And this is a standard calculation. This is very easy to do in scSTREAM. and we perform that systematically and give those numbers to our customers or their customers to evaluate their final design. So really this SiP ends up being one of those little components in a much higher level, much bigger assembly. Okay. Again, based on the type of heat that we need to dissipate, we're going to have to make some judgment calls, or sometimes we're just going to be forced into using a particular type of cooling. So we can very quickly, using the same model, look at conduction, convection, liquid cooling, heat pipes, different other types of cooling or mixed cooling, cold plates. So all this is part of our thermal analysis or thermal verification and design trade studies. So once we're happy with the thermal design, we unfortunately have to go to dynamics. And dynamics is where all those pretty and neat electronic systems and solder balls and components get really in trouble. This happens often, particularly random vibration in harsh environment. This is typically a fatigue problem, so we have to pay close attention to that. And again, for this one, we built some very detailed dynamics model in MSC Apex, almost exclusively brick models. It turns out that the geometry of those things is very conducive to using brick elements, and we model every solder ball, every solder, every landing area, all this to look at all the possibilities of fracture and fatigue failure. And we have, several orders of magnitude as far as scale between a big die and the tiny little solder balls. We have some of those designs, we have 50,000 solder balls to look at. And we looked at, it's not very difficult to mesh in Apex, so we're capable of doing that. We have, the hardware to handle it, so we're just fine. It gives us, very good models, the ability to look at everything. Sometimes we get some surprises. We see some dies that we didn't expect to have problems, and it turns out because of the vibration environment or shock environment, the dies are too close to each other and start hitting each other. So now we have issues and we need to redesign. We catch this early on with our dynamics models. And one of the nice things that came to play a couple years ago with MSCOne was CAEFatigue, particularly in the vibration, in the frequency domain. This is unmatched fatigue calculation abilities and speed, and this is tremendous for us to be able to pick any part of the model, particularly all the solder joints, and say, well, tell me how long it's going to survive. And again, those environments, military environments, so the mill standard 810, those environments are designed to represent a service life of 5 to 10 years in a military environment. So they're extremely harsh in terms of level, in terms of duration, and so it's critical that we calculate this very well, as again, you can't have a failure on the field. It's not exactly like a cell phone that you call the hotline, complain about the failure. You actually have a tank that cannot perform anymore, or radar that cannot perform. So it's a lot more dramatic than a simple failure of a consumer electronics product. So the next thing we look at, and in fact, this is probably one of the biggest problems encountered in the electronics world, is the solder joint fatigue. And so there's two types, typically. High and low cycle. So the highest cycle fatigue is, again, vibration, random vibration, sine on random, depending on what kind of vehicle we're looking at. Typically stress-based, frequency domain, CAEFatigue. No problem there. The low cycle fatigue is something that's a little bit more complicated, as as a, it's called low cycle fatigue. We're dealing with lower count of cycles, but higher chances of failure. Typically, a high cycle fatigue solder would live for hours in millions of cycles. A thermal cycle extreme, and it's usually minus 50 to plus 100 degrees, or this kind of ranges, you're expected to live 500 to 1,000 cycles. So the fracture, the failure is much more pronounced and much more rapid, if you want. And this is all strain based. We're approaching it for most of the cycles. We are actually creating plastic strain already, so we're plastifying most of the balls, or the corners at least, in many ways. So we use for this, or we use Marc, MSC Marc, to build detailed models of the BGAs. Sometimes a subset of the whole thing, but very very detailed. Thermo-Mechanical, a transient model, non-linear, that includes plasticity naturally, that includes thermal time effect, so the relaxation of stress over time. This comes to play in our thermal cycles when there's the dwell time of the thermal cycle and the rate of change of temperature. So all this is built into our model. And as far as calculating fatigue, we used either custom subroutines or Excel post-processing tools to do the calculations. So in conclusions, we are very happy with MSCOne and the tool set that it offers. We have a multidiscipline team, and everybody feels well equipped, being nonlinear, being dynamics, being modeling, thermal, rapid thermal, and everybody is very happy with that. I think we've seen over the years that MSC Apex and Nastran offer probably one of the fastest modeling, and certainly one of the most renowned dynamics analysis. Marc is a very high-end nonlinear tool. CAEFatigue probably doesn't have much of a competition. It's very specialized analysis, very high performance, and best of all, we are equipped with AMD EPIC and Threadripper HPC environment. So we have a heightened number of core, both on workstation and servers, and all of those tools scale up so well that we really see a benefit in having a big HPC environment. So as far as where we go from there, so while we continue using our tools, and we were expecting that MSC would improve performance and functionality in the tools that we already use, but further, we already know we have access to products that are fairly unique, that could augment our abilities. And there's three that we have in mind. And the most obvious one is the co-simulation between Nastran and scSTREAM. What we'll do with that, what we want to do, is to model the solder reflow, model the quasi-liquid state of the solder during manufacturing. This is important to us. This allows us to, or this will allow us to predict manufacturing defects, like a poor landing of the die, getting either sideways or not sitting properly on the carrier. We have seen an application there that would make our job far easier, particularly in the trade study side. Odyssey seems like a tool that we could take advantage of very rapidly to allow us to come up with better designs, better options, have a better understanding of all the variables playing together and how to make better decisions. And lastly, and we use SC Flow already, but we have a lot of studies in mind currently for different cooling technologies for all systems. This is something like oscillating heat pipes, for instance, and things like this.